Right, ladies and gents, welcome to this week's Geotalk. What a fantastic audience. Thank you all for joining us, both online and in person. And it's wonderful to welcome Laurence Robb to the floor today. Laurence is, of course, a visiting professor here in the School of Geosciences. He's also based at Oxford University. And he was a member of the school for many years, heading up EGRI for a long time, and the director of EGRI as well as a staff member here. And as many of you will know, he is legendary for writing the book on ore deposit geology, or ore forming processes, of which I think there's a second edition which is recently out, so you may want to read that. And his work in many different metallogenic provinces around Southern Africa, but also around the world. So it's fantastic to have you, Laurence. Thank you for all you contribute to the school, and we look forward to hearing your talk tonight. Over to you.
Thanks, Grant. So it's great to be back here. I used to sit there in the 70s.
Laurence, you have to speak microphone.
Right, here, this one.
If you just speak here, you'll be perfectly fine. Here's the master point,
Right.
and the key to move forward. Okay. I know. There we go.
Okay. So as I was saying, I used to sit over there in the 70s, and then I used to stand here for about 10 or 20 years in the 80s and 90s. But it's been probably 20 years since I was back in this room, so it's great to be back. So today, I'm going to be talking about things that are extremely old, Archean rocks, in that context. But I need to kind of confess that that this work, or not all of it, some of it was done quite a long time ago. In fact, when I was a MSc and a PhD student in this department, under the supervision of Carl Anhauser, who's sitting in the front here. And Carl is very much a kind of a co-author to a lot of what I'm going to be saying today. But it's not only going to be about old stuff that was done a long time ago. There's quite a lot of new data, particularly geochronological data, which I'll use. And what I'm planning to do is kind of revisit the crustal evolution of the copper craton as seen through the eyes of the granites in the Barberton region, and then try and put that into a bit of a plate tectonic context, if that's possible. So we know more or less what the age of the solar system is, because we've been able to date rocks from the moon and also from Mars, and the solar system is a little bit over 4,600 million years old, and people have even been to the moon, as you well know, to collect material from there, and of course we've got material from Mars as well. The geology of the moon and Mars and other planets in the solar system, of course, pretty much frozen in time, so that the rocks that you see there are pretty much the rocks that formed in the very early stages of those planetary evolutions. That's completely different, obviously, on Earth, because we have water and we have plate tectonics. And those processes are constantly active on the Earth's surface, so that the Earth's surface evolves over time, as we all know. So the preservation of very old rocks on the Earth is actually very rare. And there are very, very few places on Earth where one can study the very early parts of crustal evolution particularly well. The Pilbara Craton in Western Australia is one such area. Of course, the other area that we're much more familiar with is the Barberton mountain land here in Southern Africa. Now, the oldest rocks that we know about, at least.
Laurence, you have to go closer to the microphone. If you stand right there, you'll be close to training.
Okay. So the oldest rocks on Earth are, at least that we know about, are the Acastonices, which are just over 4 billion years old. This is a small segment of northern Canada. And this is where actually some rocks of that age actually exist. There is older material, I forgot to say from the previous slide, and that is, of course, detrital zircons that have been discovered in, for example, the Jack Hills conglomerates of Western Australia. This is a 3 billion-year-old sedimentary sequence which contains detrital zircons, which are 4,400 million years old. So that's the oldest material on the planet that we know about, but those are individual zircon grains, detrital zircon grains in a conglomerate. And as I say, the oldest actual rocks that we know of are the gneiss at 4 billion. And so, as I said, remnants of these very ancient segments of the Earth's crust are very few and far between. And the reason, of course, is that a lot of the surface of the Earth that is very old was obliterated during the late heavy bombardment at about 3.9 billion years old. But even so, even between or subsequent to 3.9, there's very little preserved material that is early Archean in age on the planet. And again, the reasons for that are water, plate tectonics, and the recycling, constant recycling of material on the Earth's surface. Unlike, obviously, the situation in, for example, on the Moon or in Mars. So one of the very few areas where we do have a really great record of the early Archean, extending for close on 1,000 million years of well-preserved Earth history is the Barberton mountain land. So you can see here on the photo, this is the Barberton greenstone belt. But not only is that extremely well preserved, but for 100 kilometers to the north and 100 kilometers to the south of the greenstone belt, we have a sequence of granites which are equally well preserved and which record a very good history of Archean crustal evolution on the Carpal craton. So it's those granites which I'm going to be talking about today. So this is a very simple map, and I'll come back to this a few times, showing the main granite types in this area. I thought I'd just mention that a lot of people have contributed to the understanding of these granites. So, as I say, back in the 1980s, it was Carl Anhauser and myself who did quite a lot of work during the geodynamics project on the granites. That was followed by some very detailed geochronological studies by people like Sandy Kano and Don Davis at the University of Toronto, who provided a really great chronological framework for this region. Then people from Stellenbosch University, for example, Alex Kisters, Gary Stevens, John Clements, have done a lot of work on the granites in particular in this region. And then more recently, there's been work done by Don Lowe and Gary Bailey from the United States, and also from Jean-François Moyenne at Saint-Étienne in France, who recently has done some fairly detailed work on the granites. So there are a lot of people that have worked on the granites, but it is certainly true to say that there's a lot less work that's been done on the granites than on the greenstone belt itself. For obvious reasons, obviously, there's mineralization in the greenstone belt. There's a record of the evolution of life in the greenstone belt. It's much more diverse. So it is generally the kind of thing that people do study in more detail. So there has been a bit of I guess, an imbalance in the knowledge of the granites as opposed to the greenstone belt. But as I say, as I'll try and show you, we do know quite a bit about the granites as well. Okay, so how old is the Barberton greenstone belt? And that's a question that a lot of people have spent quite a lot of time on, in particular people like Alfred Kroner, who spent a huge amount of effort trying to find very ancient zircons in different parts of the world. Certainly the oldest zircons that have come out of Barberton were effectively discovered by Gary Bailey and Don Lowe in their major program in the Barberton greenstone belt back in 20 years ago. And they've discovered these very old 4.1 billion-year-old zircons, of which there are 11 out of several thousand that they analyzed. And these come from the Menden Formation, which is the very topmost part of the Onkelbach group in the central part of the Barberton greenstone belt. So there are zircons in the belt which are 4.1 billion years old. Where those zircons came from, we don't know, because there is nothing preserved that we know about of that age in that region. But somewhere there must have been at some time. It's either been consumed or it's buried somewhere, and we have yet to see it and find it. So there is material around that's essentially greater than 4 billion years preserved in the Barberton greenstone belt, but the rocks themselves are not there any longer. Probably the oldest material that we've got in the region is this Phtholitic Knights from the ancient gneiss complex in Swaziland. This material was dated by Rob Bolha, and this is material which is 3,560 million years old. And this is part of the ancient gneiss complex and old Phtholitic and Trontomitic terrane in the central part of Swaziland. So this is probably the oldest rock in the region, and not necessarily in South Africa, but certainly in the Barberton region. Other very ancient rocks in the greenstone belt itself is parts of the Teersprate felsic volcanics, which are also 3,550 plus or minus in age. So there is some very ancient material around, as old as 3,500 and slightly more in the greenstone belt. If you have a look at the distribution of ages, these are all published ages that we could find, population put together by Mark Pujol, of granites in the region. You can see there are some really quite clear patterns here. And you can see that there are these two peaks here labeled TTG1 and TTG2. TTG stands for tonalite trondhjemite granodiorite. This is the acronym that we use for really the oldest style of granite platonism in the Archean terranes. You can see obviously there's stuff which peaks at around about 3,450 million years old. And there's another peak of TDG platonism at about 3,200 million years old. So these are the two principal events where tonalite and trondhjemite magnetism occurred in the region. There's another major peak at about 3,100 million years old. This is the so-called GMS suite. GMS stands for granodiorite, Monzo, granite syenite. These are the next generation of granites in the region. They're more potassic in composition, and I'll come back and describe those in a bit more detail. And then right at the end of the spectrum, we've got the late granites, which are a series of, and there are probably 10 or more of them in the region. These are younger, intrusive individual granite plutons, which typically form between about 2.8 and about 2.7 million years old. And there are several of them. As I said, there are at least 10 of these plutons, and I'll describe those briefly as well in this talk. So this is the range of granite types and ages that we have preserved in the Barberton greenstone belt. You can see just what an extensive range of rock types and ages that is, and that's what makes Barberton such a treasure in terms of Archean crustal evolution. Okay, so I'm going to start off by talking about the TTGs for 5 minutes. And as I said, these are the oldest generation of granites in the region. And on this particular map, you can see that we identify granites or TTGs that are fairly old, around about 3,450 million years old, as opposed to slightly younger ones in the north here, the Nelswifter and the Carp Valley plutons, which are around about 3,250. So those are the two ages of TTG platonism that I was talking about. There is an older pluton in the region. The Stainsdorf pluton here is actually 3,510 million years old, so it's slightly older than most of the other TTGs. And in fact, it's as you go towards the east and the southeast, there is a tendency for material to become somewhat older, and the oldest material around is, in fact, in Swaziland, as I mentioned a moment ago. So most of the TDG plutons then fall into these two age brackets that I mentioned. And there are places where obviously you can see these. Sometimes, if you're very lucky, right in contact with one another. And this is the famous Teerboom outcrop, which I mapped as part of my PhD. And here you see two of the TDG phases, in fact, two principal ones, right in contact with one another. Obviously, an older phase, which is compositionally banded, which we see on the right there. These tonalites are 3,460 million years old. And this compositional layering, you can see, is truncated by this contact here. And this tonalite, this trondhjemite pluton here is 3,201 million years old. So here we have the two TTG events really superimposed, and one intruding the other. So no question there are at least two generations, and that the one intrudes the other. That's all in the south of the Barberton greenstone belt. As I say, those outcrops I was talking about are essentially in the southern part of the greenstone belt. Elsewhere, and in the northern part of the greenstone belt, and this photograph was taken about 100 kilometers north of Barberton. It's actually in the Nelspruit granites, which I'll talk about. But here you see these old gneissic xenoliths caught up in the middle of the Knellspate granite. The Knellspate granite, 3,106 million years old. But these remnants, which were again dated by Sandra Camo, 3,300 million years old. This is not an age that you see in the southern part of the greenstone belt, but obviously you do see it in the northern part. So possibly as you go northwards, there is material, TTG material, there's not the same age necessarily as what we see in and around Barberton itself. So there is a spectrum of ages, 3.45, 3.3, and 3.1, representing different episodes of tonalite and trondhjemite intrusion in the Earth's crust. And these are all part of that early phase of granite magmatism that started to build the foundation of the Karpval craton. So these TDG Protons, if you look at them, they all look remarkably similar. They're all tonalitic or trondhjemitic in composition. In other words, they're dominated by quartz and plagioclase with a little bit of biotite and sometimes hornblende. So although they look very similar, if you look at their trace element compositions, you see that they are quite different one from the other. And those trace element characteristics can be used to tell us a little bit more about how these rocks formed, and particularly interestingly, the depth at which they were formed. Some of the trace element characteristics of these bodies do indicate something about the depth, as I'll show you in just a moment. Here's a plot of some of these TDG Protons in the Barberton region. Most of them you can see have silica contents greater than 70. So these are trondhjemites, quartz, plagioclase, biotite. But this particular body here, shown in these brown circles, that's the Carp Valley Pluton. That is tonalitic, so it has composition, silica values less than 70. So less silicious, but still plagioclase, quartz, hornblende, biotite. So these are all the same rocks, but they obviously have different characteristics. If you plot the strontium versus yttrium ratio of these TDG bodies against their yttrium contents, as Jean-François Moyen did a few years back, this plot is often used as a geobarometer, as a crude geobarometer, as an indication more or less of the crustal depth at which these magmas were formed. And you can see there's quite a range, ranging from sort of fairly high pressure melts, certainly well in excess of 20 kilobars, to much lower pressure melts, which formed sort of in the region of 10 to 12 kilobars. There seems to be a range in depths in the Earth's crust where these things were generated and were emplaced. So there are variations in the characteristic of these bodies when you start looking at them in detail. It's also very clear that, and this is based mainly on experimental work, that most tonalitic and trondhjemitic rocks in the Archean were derived by the partial melting of amphibolite, of some sort of pre-existing greenstone that was in amphibolite grade, it was fairly hydrated, was buried, or maybe even subducted, and then underwent partial melting to form essentially the TTG magmas. So this is a model which attempts to, I guess, quantify the amount of melting that you would need to undergo of an amphibolite to make a typical tonalitic or trondhjemitic magma. So the starting composition on these plots is here. This is a typical amphibolite from the Barberton region. And this curve here is a sort of a progressive melt fraction. It's derived by melting that amphibolite. And the average tonalite, trondhjemite TDG from the Barberton area plots around about here, around about 25% melting, which is kind of an estimate of how much melting would have to take place of pre-existing greenstone and phtholitic material to make the TTG suite. You can also see on this the scatter of chemical compositions that characterize the TTG suite, and this is almost certainly not just partial melting, it's probably a function of some degree of crystal fractionation in the pluton itself. So these are some of the features of the TTGs. They seem to be consistent with derivation by partial melting of pre-existing greenstone belt type material probably largely amphibolitic. There are examples of high pressure TTGs, particularly, for example, in central Swaziland, stuff that Gary Stevens and Alex Pfister have worked on, where the residue is almost certainly CPX rather than hormone. But that's a different story, which we won't get into today. So that's just a quick snapshot of the TTG suite, what they are and how they form. Moving on in time to essentially the GMS, the granodiorite monzogranite cyanide suite. This is essentially the rocks which are shown on this map in blue. And there are three major batholiths which have been studied over the course of the years. There's another major batholith in Swaziland itself, which is almost completely unstudied. But we have a lot of information on the Heerenveen, the Impaluzy, and the Nelspruit batholiths from work that was done already many years ago. Interestingly, although these are aerially very extensive granites, you can see they cover essentially huge swaths of Archean terrane in the region. They're typically very thin, sheet-like intrusions, typically only 1 or 2 kilometers thick. They're mid-crustal, and they're sort of like large sills, which intruded through the TDG and then consolidated and crystallized in the mid to upper crust. Although they look very extensive, they're actually fairly thin in terms of their volumetric capacity. These rocks are, although they're extensive, they're all formed pretty much at the same time, around about 3,110 million years ago, plus or minus about 10 million years on either side. So the total range of emplacement of these huge swaths of magma was typically between about 3114 and 096, so over about 20 million years or less. They were all emplaced at that time. So this is obviously a very significant and very important event in the evolution of the craton. Clearly, there were huge areas of the craton affected by this particular event. This is what they look like in the field. This is again in the southern part of the greenstone belt, looking southwards towards Swaziland. The Land Rover, this is Carl Hanhouser's favorite old Land Rover. But the low-lying terrain is all TTG, looking southwards towards Swaziland. The edge, the northern edge of the Impaluzy batholith. But you can see these very much more resistant, more potassic-rich rocks. These are essentially the quartz monzonites of the Impaluzy batholith. Typically, as I say, those rocks are 3,010 million years old. This is what they look like in the field. This is actually the Impaluzy batholith, where it's in the middle of it. This is actually underneath the Impaluzy batholith in Swaziland. This is actually looking at the area through which the magmas must have passed on their way up to consolidating somewhere in the mid-crust. So this is ancient gneiss complex, sort of maybe originally low crustal material, showing the conduits of the magma as it consolidated at a higher structural level above this particular level. So this is the Impaluzy batholith passing through the ancient gneiss complex on its way to a higher crustal level, if you want. Geochemically, these rocks are very much more evolved than the TDG suite. So the red dots here are essentially the potassic batholiths. The blue dots are the TTGs. They're much more enriched in rubidium and other large iron lithophile type elements. They are clearly much more fractionated in composition. They nevertheless have their own individual characteristics. So this plot here shows the compositions of the three different batholiths. The Heerenveen in blue, the Nelspruit in red, and the Impaluzy in green. You can see that the Heerenveen is much more sodic in composition, even though it has big phenocrysts in it. The phenocrysts are largely bathytic. There's a lot of plagioclase in there, whereas the phenocrysts in the Impaluzy batholiths are largely microcline. So those very subtle mineralogical variations reflect the chemical variations of the batholiths as a whole. Nevertheless, on average, these plutons are effectively granodioritic in composition, or perhaps quartz monzonitic, and they're substantially more potassic than the TTG suite. All of these rocks are essentially 3110 MA in age. Here's just another diagram showing the differences in chemistry here in terms of strontium. Again, strontium, like for the TTGs, is a very sensitive discriminator of different pulses and against the granites in the region, it would seem. One of the interesting things about these large batholithic-like bodies is that they underwent a very pronounced internal crystal fractionation, which seems to migrate from the edges and the tops of the bathulus inwards. So essentially, what we're looking at in terms of these things is that they started to crystallize and cool on the margins, and then they progressively crystallized inwards. So there's a very prominent crystal fractionation trend that is recognized in these bodies. And this was work that was done by Spike McCarthy and I way back in, I guess, in the 1980s or wherever it was. I mean, it was one of the first attempts to recognize crystal fractionation processes in granites. Because those processes were well described, obviously, in mafic rocks, which are much hotter and less viscous. But very seldom had those processes been described in granites. And firstly, because layering is never really that evident in granites, and secondly, because the effects of crystal fractionation are much more subdued and subtle in granites than they are in mafic rocks. So this was effectively the subject of Spike McCarthy's PhD thesis, in fact. And it was one of the first recognitions of crystal fractionation processes in classic magmas. I mean, it was a major, I guess, milestone in igneous petrology that was due to his PhD work. And this was one of the studies that we used to try and demonstrate case studies for this process. This particular diagram shows two trends with an inflection point at CL there. These early trends over here effectively dominated by plagioclase fractionation, and the inflection is where K feldspar comes on the liquidus. So these trends here are plagioclase plus K feldspar fractionation in these large batholithic granites. And you can see that that the data, although there's a real shotgun of data points now, there's so much data. You can see that the plagioclase fractionation trend is dominated by the Heerenveen batholith, whereas the later fractionations are essentially Melspray plus Impaluzy. Again, reflecting the fact that Heerenveen is dominated really by plagioclase phenocrysts, which controls the fractionation of these magmas. And then finally, what I'd like to talk briefly about then are the late granites. The 10 or so late granite plutons that essentially terminate the history of granite magmatism in the region. And interestingly enough, these 10 odd plutons fall along two very distinct linear arrays. The westerly array, made up by these plutons here, these four plutons here, these are effectively what Michael Meyer and I refer to as high calcium granites, and they're somewhat akin to I-type granites derived by the melting of igneous precursors. Whereas the easterly array are characterized by these pink plutons here, dominated by these low calcium granites, with the exception of this one Quetta pluton here, which kind of spoils the whole picture somewhat. Should have been on the other side, but for some reason it's on the other trend, and as I say, it really spoils the picnic. But nevertheless, there is a trend. Most of the granites in the western array are I-type granites or I-type-like. They're all 2720 million years old. Most of the granites in the easterly array are high calcium, somewhat similar to S-type granites, and with the exception of the one, they're typically much more akin to S-type granites. So it seems to be some sort of a fundamental distinction between the two granites in the two different arrays. That's a little bit like what we tend to see in other parts of the world, particularly in more recent orogenic belts, like the Andes and like in Southeast Asia, which I'm fairly familiar with, which is why I'll show you that this example, this is a region that Michael Searle and I have been working on for many years. And again, you see the same thing, linear belts of granites. Some of them are I-type belts and some of them are S-type belts. All related to an active subduction zone, which is just to the west of that arc of islands, the Andaman Trough, where there was a huge earthquake in recent years. So that's the subduction zone. And all of these granites here are the product of ongoing subduction since the early Mesozoic and active even to the present day. So these are very long-lived systems which have given rise to these huge belts of granites. This is of course where the tin granites of Southeast Asia come from, as well as other porphyry I-type granites as well. So these are highly mineralized granites associated with modern day subduction. Those belts, as I say, are somewhat reminiscent of the kind of belts that we're looking at in these late Archean examples from Barberton. So there's the first indication here, possibly, that maybe there's some sort of plate tectonics process, some form of subduction might have been prevailing in this region at that time. And I'll come back to that. So here's what some of these plutons look like. This is the Impaluzy pluton, the northernmost one, north of Barberton, 2740 million years old. And these are so form very discrete, very obvious plutons. They're essentially all granites in terms of their composition, and they are very obvious in terms of terrane and physiography. When you look at their geochemistry, they subdivide very clearly into two populations. Populations which Michael Meyer and I called high calcium and low calcium. We would have liked to have called them I-type and S-types, but we were reluctant to do so because where there are other I-type and S-type granites, it's very obvious that the S-type granites are always associated with metasediments, and so they clearly are S-types. Whereas here, these so-called S-types, there's no obvious association with metasediments, and they're all associated with igneous material. So whether they are genuinely S-types or whether they just look like S-types because of their petrogenesis is something we haven't really yet resolved. Nevertheless, they're not absolutely clear-cut S-types, although, as I said, they certainly look like S-type granites. So as I say, there are these two populations very clearly identified, and one sees them on literally any plot that you care to talk about. This is a plot after the work of Buchholz and Spencer, which divides granites on the basis of whether they were derived by essentially biotite dehydration or muscovite dehydration. In other words, a proxy for possibly I-type in terms of biotite dehydration or S-type in terms of muscovite dehydration. So clearly, again, those links and those analogs are there. But whether these low calcium granites, as I say, are genuinely S-type, I think the jury is probably still out on that. They form at different temperatures because of the different breakdown reactions involved. It's also very clear that the high calcium I-type granites are less fractionated than the S-type granites, which tend to be much more highly fractionated. And at least one of these plutons, the Cincinnati pluton, is mineralized. It contains enriched pegmatites and hydrothermal veins that have lithium and tin mineralization associated with them. So this is probably one of the earliest examples of magmatic hydrothermal tin and lithium mineralization on the planet associated with the Cincinnati pluton. In terms of the origin of these two different granite types, again, one can play around with partial melt models, which I have done here. These the red spots here are the data for the I-type high calcium granites. The green ones are the low calcium S-type like granites, and these are essentially model melt curves. The first one is effectively a batch melt model of a potassium bathulus-like source, like the Nelspruit or the Impaluzy bathulus. So if you melted those pre-existing rocks, you would make a melt which looked very much like the Impaluzy pluton, for example. The other population of granites is clearly very different, characterized by these very low rubidium contents. And the only way you can derive partial melts of that kind of composition with those kind of trace element compositions is and the only thing I could find in the literature to melt was in fact the fig tree-like sediments, fig tree-like arkoses, which is obviously a sediment. So these low calcium granites can be modeled by melting a metasediment. Again, as I say, they look like S-type granites because they don't necessarily, they're not obviously related to metasediments. We have in the past been reluctant to call them S-types. for that reason. This is a plot of heat production against age, and effectively it's a proxy for the potassium uranium, combined potassium uranium and thorium content of the granite magma. You can see that most of the early TDGs and the GMS suites are fairly low heat productive, but the late plutons are very much more enriched in radioelements, and they produce radiogenic heat and have done so ever since they formed. This particular pluton, the Cincinnati pluton, whose age plots here at 3,000, just over 3,000, and this is a mistake. It wasn't plotted as a mistake. If you look at the published age, it's essentially 3,100. The reason is that the samples were taken from essentially right on the edge of the Cincinnati pluton, where it's in contact with the Pig's Peak bathulus, which is 3,074 million years old. This Cincinnati pluton doesn't have any zircons in it, so the zircons that were analyzed almost certainly Pig's Peak zircons, which is why it gave an age of 3,070. This is almost certainly not the age of the Cincinnati pluton. It's probably, instead of being there, it probably should be somewhere at 2.8, like the rest of the low calcium plutons, and that dating needs to be redone. But anyway, that's I guess just an anomaly. The fact is that that the late plutons effectively are very heat productive, and at least one example of those plutons is mineralized with tin and lithium. So really then, I guess what we now need to do is just put this little story together, and there are several ways of doing that. One of the ways, which Nick Gardner did, is to effectively compile the age and the hafnium isotope characteristics where we have that data. And it's interesting to see that, certainly all the granites that occur to the north of the greenstone belt seem to fall on an array which is which he called a TTG reworking trend. In other words, if you look at some of the early TTGs, there are 3.2 billion year old TTGs. They are collinear with the GMS suite, and collinear at least in terms of late plutons with the Impaluzy pluton, suggesting that maybe these late TTGs were reworked to form the GMS, which itself was reworked to form the Impaluzy pluton. So that is one suggestion from the hafnium isotope data, that we're looking at successive reworking and melting of material to form subsequent and younger events. So one can, I guess, summarize the features of these granites in a cartoon. So these are essentially different snapshots at different times. This is obviously 3250 and 3450. These are the two ages of the TDG plutons. And these are emplaced by essentially what processes that are referred to by people like Martin van Kronendonk as sagduction. In other words, where we have high density mafic material overlying lower density tonalitic material, that's gravitationally unstable, so it overturns, and you get diapers of TDG material placed into the base of the greenstone assemblage, which is pretty much how we see the emplacement of these TDGs, as sort of a solid state, almost gravitationally diaperic style of emplacement. So that seems to be the emplacement style for the early TDG and the later TDG events. At 3110, this is obviously the period in time when the large potassic bathulus were emplaced. Again, these bathulus would have been essentially sort of mid to lower crustal partial melts, probably of earlier TDG-like material. I guess what we really don't understand, though, is what precipitated that partial melt event. Alex Kissers refers to crustal thickening and exhumation, which is certainly a process which could cause melting of the lower crust. But what exactly caused the exhumation of the crust and the melting event, we actually have no idea. So the reason or the cause of these huge 3,100 million year old bathulus and the melting that created them is something that we know and understand very little about as yet. And then finally, obviously, the late plutons, the high calcium and low calcium, reminiscent of S and I type granites, these could be related to subduction type processes, because it's exactly these kind of granites which we see forming against and adjacent to subduction zones ever since the late Proterozoic and right through the Paleozoic. So this might well be the signal, I guess, for the onset of plate tectonics, at least in the Barberton region. So if you summarize the whole thing, and what I've done is I've borrowed here a diagram from Peter Kaywood and Chris Hawksworth's work on crustal evolution, and then added my own ages and a few other events to make it look as though it's for Barberton, and which it is in this case. So when you summarize the whole story in terms of granites, we start off at sort of in excess of 3,200 million years ago, so back to 3,500 million years ago, with a relatively thin crust, where essentially granites were forming by the sag duction and partial melting of pre-existing amphibolitic material to make essentially the TTGs. And this obviously essentially built the crust from a relatively thin, predominantly mafic veneer to something that was more continental-like initially in these very early Archean times. As the crust thickened, and possibly as it was exhumed, again, a second major period of melting of the lower crust to make essentially the potassic bathulus, the so-called GMS suite. Again, what caused the exhumation, we don't really know, but certainly by 3100, the craton and the Earth's crust was very well defined. It was probably at least as thick as it is now, and it was certainly strong enough to be able to accommodate significant sedimentation like the Witwatersrand, the Pongola, and the early intracratonic basins that formed subsequently to 3,100 million years ago. Again, no actual subduction that we can recognize, but by the time you get to 2,800 million years ago, and you start making the late plutons, both the high calcium and low calcium ones, these are granites which quite easily fit into a plate tectonic and a subduction paradigm. So these wells could well have formed by subduction, which means that plate tectonics on the Carpal craton would have started somewhere between 31 and 2,800 million years ago. Exactly when, I guess, it still needs some clarification. The early phase of tectonism has been referred to as drip tectonics, where essentially material was gravitationally overturning and these high density mafic things were dripping back down into the lower crust. Whereas later on, it's obviously more akin to plate tectonics. So clearly, the granites do have quite a story to tell, not only in Archean, in the Barberton area, but for Archean crustal evolution in general. Thanks.
Laurence, that's fantastic. Do you have any questions from the audience here or the audience online? We will start with the audience here. Rob and then Roger. Rob, you have to speak quite loud.
Yeah, thanks for the brilliant talk. You were wondering what was the melting or reworking of the earliest TTGs. You've also shown that the younger granites are enriched in the heat elements, whereas the older ones be poor. It's known from lower crust, for instance, in the Wyoming craton, that if you have lower crust sitting with a lot of high-producing elements, it's unstable, so it has to melt with the high-producing elements. That could explain why the TTGs are depleted with the high-producing elements. And the later state granites are actually enriched. So that's just a comment. The second thing is, I think it is known from the work by Sobolev that subduction and plate tectonics may have started at about 3.2 based on marker isotopes. And I think the third question I have is, you showed the Epson Heffling values for the earliest TTGs that were quite negative.
Yeah.
Well below Sure. Does that mean that they are remelting products of very ancient crust that is no longer preserved? Question for you.
Yeah, so I mean, if you go back to Nick Gardner's diagram, can we just go back one, I think, no, two, yeah, that one.
Yeah.
So there's the stuff to the south in the ancient ice complex, and that seems to be somewhat different to the trend in the northern part of the Greensand Belt. So whether there was older material that might have been somewhat akin to that, but would have had essentially positive epsilon hafnium, and we don't know about it, or whether in fact there are simply different crustal segments that evolved in a different way in terms of hafnium. I don't really know the answer to that, but it's an intriguing thing. I mean, where are all the products of the melting of the ancient gneiss complex? Possibly in northern Pongola or somewhere like that. What was the other question, Rob?
I think that was my main question. How would you explain the effects, the negative epsilon values of the very ancient gneiss complex? Because it would suggest that there was pre-existing process.
Yeah.
Very early on.
Yeah.
Which we don't know.
Roger.
Thanks, Laurence. Also, two-part question. So the first one is you spoke about the high and low calcium granites being possibly having an analog in Sumatra, Indonesia. There are those granites, in the Sumatran case, are they all the same age? Because the ones you're talking about are 100 million years apart in Barberton.
Yeah. So when you resolve those belts, they're not just two belts; they're actually a lot more of them. But any one belt, they're more or less the same. But the belts in Southeast Asia young progressively from east to west. So the oldest belts which are early Mesozoic in age are in the east, and the ones which are still forming at the present day in the Andaman Trough are essentially in the west. So essentially what seems to happen is that the subduction zone is rolling back, and it's creating successive parallel arcs as the subduction rolls back.
Okay, so the second part then is to bring it back to the craton. 2830 to 2720 faces you kind of towards the end of Central Rand Group and whatever the Pongola is. We see a major change in tectonism and the bits, probably relates to what's happening further west around the Colesberg lineament and whatever. And then 2720 is the Blackberg event, which is a major rifting event in the central parts of the craton. And at the same time, you look at the Limpopo belt, at about 27, you've got the southern marginal zone coming on. So is there any attempt to try and reconcile the Barberton stuff with the rest of the craton, where we're getting these snapshots of different levels and different sort of environments?
Yeah, so I haven't done that, but I think it would be certainly a very useful exercise. But I wonder if maybe Armin Zay's work hasn't touched on some of that, because I mean, there's quite a lot of stuff that he's done, which I haven't really referred to at all here because just too much of it really. But I mean, I think there may well be some stuff like that. It might be worth looking at his work. But other than that, I'm not sure that kind of thing's been done at all, and it might be worthwhile doing something like that.
Scott, yeah, go for it.
Is there any difficulty in getting hydrated amphibolites to the base of the crust or deeper? You know, like, do you know, are there any models or something that support getting a lot of water to the base of the crust where it can melt, right? Like in the early, for the early stages of the model. That's always a little bit tough to me, but I don't have the gel.
I mean, sure, I think if it was all cladopyroxene or something, obviously there'd be no problem. And obviously, if it's amphibole, if it's warm, then it's still reasonably dense. So I think you could still overturn an amphibolite because it's certainly denser than a rock that's dominated by, say, plagic phase and quartz. So even though it may not be as dense as an olivine CPX bearing residual rock, I think it would still be sufficiently dense to overturn gravitation. That would be my sense.
I know Tarascaria and Sisovos showed some numerical modeling that can happen quite easily.
Okay.
For an amphibolite.
Yeah. Okay, Jagamoy, and then we'll take Lou, who's online.
So one of my questions then is actually...
Okay. Am I audible?
Hang on, Lou. We'll just have Jagamoy first, then you, okay?
So one of the questions is, do you believe that there was some kind of proto-alien crust, if there was anything in the Phtholic, because you have the alien circle?
Yeah, look, I do. I think somewhere there's going to be much older material. I mean, those Zircons have had to have come from somewhere, and at 4.1, and unless so I do think that maybe lurking somewhere deep in the ancient gneiss complex or buried, some of this material might actually now be back in the mid crust. But I do think that there's got to be some much older stuff. And we've got to either find it if it's there at all, I mean, this is what, as I mentioned earlier, this is what Alfred did. I mean, he was really passionate about looking for the oldest zircons. He did find the oldest zircons in the world in Western Australia with Bill Constant. I mean, he was very good at that. And he spent a lot of time, not so much in Barberton, but in Swaziland. He spent months in Swaziland looking for greater than 4 billion year old crust. And they did, the hell out of those rocks but he never found it. Not that I know. Anyway.
The other question is actually why and how would you account for this switch in style of DDG magnetism to K-Felsic organism or plutonsism? Why do you think this transition at 3.2 or 3.1?
Yeah.
Why do you think this transition starts from solid splits to potential splits?
I mean, so I don't know the answer to that. And the reason is that it's a very difficult thing to answer anyway, is that if you look at the time intervals between the end of TTG2 at 3200 and GMS at 31, that's 100 million years. If you look at from the end of GMS to the oldest late plutons, that's 270 million. So there are huge gaps in time. And so these events are not really related in any way. We're looking at 3 snapshots of the Archean of 1,000 million years of Earth history. We just happen to have windows into 3 of those sets of events. And what was going on in between, of course, we don't really know. And either you make inferences from other Protons, other Archean Protons elsewhere, where maybe they do have that interval covered.
Yeah.
But certainly, it's not a complete record of Barberton. I should never have given that impression if I did. It's definitely just three windows into a sequence of events, which is a much bigger story.
Yeah, because at 3.1, there's also like a very dominant magnetism event.
And as Roger mentioned, there's all sorts of other things elsewhere in the Proton, besides just what's going on in the environment.
Thanks, Jagamoy. Okay, Lou, you're up.
Hi, Lou.
Okay, am I audible?
Yeah.
Okay, cool. Laurence, I'm sorry to say, but I have never liked this sagduction story for the older stuff at all. I think the evidence for it is really very, very shaky, and I don't buy it. But the latest piece of work that relates to your story, I think, is published by Don Lowe and his friends. I think one of them, the lead author, I think, is from Harvard, where they were looking at zircons from detrital zircons from one of the older the older sediments there, and they I think what they did is hafnium isotopes, maybe some other things. I don't remember the details, but their story provides a much more convincing case for the start of subduction to be more like 3.8 rather than 2.8. So they've analyzed a lot of these really old zircons from Barberton, and that's a story that I would prefer to buy.
Yeah, so I mean, I think a lot of people do push subduction and plate tectonics way back into the early Archean. I guess the kickback is that the sort of the tectonic style and the nature of the rocks. I mean, although they're broadly calc-alkaline and I guess you can find equivalent rock types in younger origins, but nevertheless there is still something unique about the way in which the crust developed in sort of the early to mid Archean. And I guess it's that fundamental difference which drives models which I guess essentially eliminate conventional plate tectonics from those processes. And also, so my question to you then is, if you don't like the overturning idea, I mean, nevertheless, you do have dense material overlying less dense material, and that is gravitationally unstable. So that itself can't really argue against, can you?
Yes, I can. It's not gravitationally unstable. You have a 7-kilometer object called the Bushveld complex, which has been there for 2 billion years, and it's not unstable. So this idea that it's gravitationally unstable, I think, is crap.
Okay, fair enough.
Okay, a discussion for coffee on Friday, Lou, if you join us in the department.
I'm drinking tea nowadays.
It's a pity of that here.
Okay, do we have any more questions from online or in the audience? Okay, the last two, Judith,
Just
and then
a quick one. You seem reluctant to that's English I and S type, as though you're using the Chapman White original igneous and sedimentary protons, but they did amend that later to infracrustal and supracrustal. So it seems to me as though your granites do fit in the INS type.
Yeah, I guess so. I mean, that's a good point. I suppose if you call them supercrustal as opposed to sedimentary derived, that would make it a lot easier to use that conventional nomenclature.
Well, that's why they changed it,
Yeah.
because of scenarios like you're describing.
I think the other fundamental problem is that at 2.8, or even at 2.7, or even a bit younger, you presumably you have to make an S-type granite. You need to essentially bury a lot of metasediment into the base crust so it can melt. And that it's not obvious as to how that actually happened in the context of here, because most of the big sedimentary sequences like the Wits were still very much there. They were fairly stable on a craton, which was effectively, is renowned for its stability. And how you get those metasediments down there to make genuine S-type granites derived from sediments has always been the reason why we've never called them S-types. But if it was supercrustal rather than sedimentary, then you can put all sorts of things in the supercrustals and maybe get over that little problem.
Yeah.
Okay, one last question.
Since the TTG granites are regarded as the oldest type, which fall under two different age brackets, as you said, how can we use them in order to explain or to describe the type of environment it was when they formed?
So why two events in the same process? Yeah, because well, if you look at the age of the greenstone belt itself, you'll notice that there is an older 3.45 to 3.5 section of supercrustals, and then there are younger greenstones that are much younger, that are 3.2. So it's possible that you're loading dense material onto the upper crust in two distinct events, and that's why there are two events of TDG as well. So I guess the answer to that is that the greenstone belt itself is made up of two distinct events, not one. So you can overturn twice rather than just once.
Okay, thank you. That was a fascinating discussion. Yeah, we can. So next week's talk is given by Nicolas Saint-Hilaire, who is from ETH in Zurich, and he'll be speaking about the world's highest grade cobalt resource in Morocco, formation associated with supercontinent breakup, biotic crisis, and basinal brines. So, and of course, thank you to John Hancock and CCIC for the drinks.